Okay, this is the introduction for lab number 25, and this is about the hydrogen atom. And I will tell you ahead of time that this is not an online lab, but it is actually one of the harder labs. So please give it a little bit of extra time as you go ahead and try to do this. Now, what we're essentially going to do is we're going to construct a hydrogen atom. And so what we can do is we can use this guy to represent the first couple of radii of the hydrogen atom, where what we're doing is we're saying we have a positively charged nucleus, and we're going to have some electrons that live inside of these shells, these very discrete shells that have to occur at certain orbits. And we would actually call these guys, n is equal to 1, n is equal to 2, and n is equal to 3. So this guy is going to let you calculate the orbits. Again, n is equal to 1, 2, 3. Go ahead and plug those guys in right over there. And then we can figure out the circumference of these orbits using the fact that the circumference should just be 2 pi r. So fill these guys out, and what we're then going to kind of do is say that actually these guys are behaving like waves. And so this guy is going to have some wave that kind of wobbles about, like we saw in the last simulation. This guy is going to have some wave that kind of wobbles about it, and it would be a first order wave, and it can only live at that particular orbit. So what you're going to do is I'm going to have you go ahead and take a piece of paper, and you're going to draw waves that look like n is equal to 1, 2, and 3. So this guy right over here would have maybe one full up and one full down. Go ahead, cut that thing out, and wrap it around so that way it has to constructively interfere with itself. We can do n is equal to 2, and this guy right over here, this is going to not be the best drawing in the world, but we'll see what we can do. N is equal to, or there's one wavelength and there is two wavelengths. Go ahead and cut that thing out. This is going to look a whole awful lot like this guy right here, which you probably recall from the lectures. N is equal to 3 is going to look like this. And I said one of the beefs that I had with this particular image is actually they're not kind of equidistant, and that's going to be important in a little bit. They're actually going to get closer and closer and closer. We can go ahead and calculate the energies for n is equal to 1, 2, 3, and so on and so forth. And I have you do that here, here, and here. I do have you sketch an energy level diagram, which is going to look a whole awful lot like this. Here is the energy level diagram that we kind of saw in the lecture. And go ahead and do this, and go ahead and label n is equal to 1, 2, 3, and label their energies. So that guy is going to go here, here, and here. And then I say, well, let's go ahead and calculate some of these changes in energies. And what we could essentially say is the change in energy, say, as you go from 3 to 2, would be equal to the energy final minus the energy initial. If we were to go ahead and calculate the frequency of a photon, then we would say that this change in energy is going to be directly related to the frequency using Planck's constant just right over there. And then we could calculate what the wavelength would be, and we would say that this is going to be the speed of light is equal to the wavelength multiplied by the frequency. Convert this to nanometers, please, because it is going to be more convenient to look at. And ask yourself, would this be visible? And we kind of know what the first one, or we kind of know what this would be for the hydrogen atom, so you can always check yourself on that. What color would it be? How would you know? Bear in mind that the frequencies of visible light is going to be 400 nanometers to 700 nanometers, where the lower end, the 400 nanometers, is going to be violet, and the upper end, 700 nanometers, is going to be in the red range. We can go ahead and Google a spectrum chart for hydrogen and identify the line and what should its wavelength be. It's going to be slightly different because of rounding. Then we can go ahead and look at the 4 to 3 transition. Go ahead and draw your energy level diagram. Do the same thing, energy, frequency, wavelength, is it visible, and color. And if we were to have one go from the ground state up to the first excited state, what would the wavelength be, and would it be visible? Again, this seems like an easy lab, but it has lots of calculations in it, so please do give it the adequate amount of time.